This video is about immunology as like quite an overview. This whiteboard looks mental, but inshallah I'll try and get through this as fast as I can. So firstly, if we just do a quick overview in terms of immunology, so we've got our innate immune system and our adaptive immune system. Our innate immune system, this would be more at the location. It's quite an immediate response, it's very quick and it's very generalized, so it's not specific to any specific pathogen. Then we've got our adaptive immune system. Now this is involving with our T and B cells, which are both lymphocytes. This would happen also away from the site of infection. And the adaptive immune system is also specific, and for this reason it would take longer. And we've got a complement system, which works in line with the other two. Now I'll quickly just go over the main cells again. There's a video I've got which is much longer, so it's important to watch that prior to this video. And then we've got our pluripotent hematopoietic stem cells. I'm not going to go into that too much, but that's just like where it all stems from. Then it leads to our two lineages, our myeloid lineage, then our lymphoid lineage. Myeloid, we're talking about our bone marrow. Lymphoid, of course, is lymphatic. Myeloid forms three things, differentiates into three things: megakaryocytes, which thus forms platelets; reticulocytes, which leads to the formation of red blood cells; and then we've got our myeloblasts, which leads into the majority of our immune cells involved with the innate response. So we've got our basophils and mast cells. These are quite similar. Basophils, however, B for blood, they circulate around the blood. Mast cells would be fixed in their tissues. Then we've got our neutrophils. They are, I believe, the first at the site of infection, I think. If I got that wrong, then I'll write down in the comments. Then we've got monocytes. Monocytes would then form our macrophages. Our macrophages are found in our tissues. And we've got eosinophils. Then the other lineage, we've got our lymphoid stem cells, which thus formed our B lymphocytes, T lymphocytes, and NK cells, also known as natural killer cells. So our B lymphocytes would form our plasma cells. Plasma cells are involved with producing your antibodies. Memory cells, of course, is for long-term memory and like build-up of immunity and all that. Then our T lymphocytes, that would form our CD4 cells, which would have a CD4 receptor, and also our CD8 cells similarly would have a CD8 receptor. CD4 forms our T helper cells. CD8 would form our T killer cells or cytotoxic T cells. That's involved with like apoptosis as well as cell lysis. And then we've got, like I said before, our natural killer cells. The other video expands more on that. And we've got our dendritic cells. I've placed them in the middle because it arises from both our myeloid lineage and our lymphoid lineage. So that's a very quick overview. Let's get straight back into our immunology then. So let's start with our innate immune system and our external features. So the physical immunity barriers. Firstly, I'm going to talk about skin. So in terms of the skin, we've got our sebaceous glands. These would release sebum. Sebum has got fatty acids and lactic acids. Thus, this would inhibit bacterial growth. Next thing will be our mucociliary escalator. So split the word down: mucus, ciliary, cilia. So our goblet cells would secrete mucus. The mucus would allow for the pathogens to be trapped inside, and our ciliated cells would just waft this along, including with the trapped pathogens. Next will be our lacrimal apparatus. I don't know if I butchered the name. This is involved with tears. Tears similarly with saliva, so I'll kind of talk about them at the same time. They both contain lysozyme as well as IgA or immunoglobulin A, I think. This is an antibody, and what the whole purpose of lysozyme is in both tears and saliva is it would allow for the degrading of the bacterial cell wall. Then we've got, in terms of our urinary system, the urine would flush out pathogens from the bladder area, and gastric juice, so our HCl or hydrochloric acid, would create an acidic environment that would thus destroy the pathogen. Now I'm going to go over the antibodies just so it'd be easier to link back, as well as the interleukins. So in terms of our antibodies, I saw this thing on like a YouTube short which was talking about how to memorize them. If you ever think about how to know all of them, just think of the term gamed. So you got G-A-M-E-D, G-A-M-E-D. Let's start from the beginning though. I'll reference a YouTube short a bit because I watched that prior to this. So IgG, G standing for Goo Goo Gaga. That, I think it was like Med School Bro or something, his YouTube channel. It's a really good 1 minute video covering all of antibodies. So IgG, this would be involved with neutralization and opsonization. IgG is the most abundant, and it also aids in our complement system activation. And the whole Goo Goo Gaga thing, that's, you link that with a baby. when you think of a baby, the way to reach the baby would be to cross the placenta. So IgG crosses the placenta to reach the baby, thus is involved with passive immunity. I just accidentally rubbed this out, but that's fine. They have the same structure. Next, we've got IgE, E for allergy. IgE would activate your mast cells and is involved in your allergic response. I don't know what this means. I'm assuming, inshallah, when I watch this video again, I'll probably understand it. So it's involved with T1 hypersensitivity. Next, we've got IgM. IgM is a pentamer. Bear in mind, once again, these are all antibodies. So IgM is a pentamer. So he said the way to memorize this, if you look at M, 1, 2, 3, 4, 5 pentamer. Then we've got IgM is the first antibody released in the immune response, and IgM also activates our complement system. Next, we've got IgA. IgA is a dimer. This would neutralize the pathogens, and it is found in breast milk, tears, and saliva. The guy said the way to memorize this would be you have two breasts, so it's a dimer in that sense. Next, we've got IgD, and this is membrane bound. It's involved with like naive B cell. It has a naive B cell receptor, and it supports B cell differentiation. I need to fact check that. If I got that wrong, I'll write in the comments. Next, so we've gone over physical immunity barriers and antibodies. Let's go over interleukins. So once again, a YouTube short reference. I can't remember his channel, but he said there's a guy, a YouTuber, who mentioned a good way to memorize this from interleukin 1 to interleukin 6, and that would be hot T-bone steak, cancelling out the ST part. So IL-1 would be hot T-bone EAK, because like I said, cancelling out the ST. Now IL-1 is hot, so it's to do with the fever. IL-2 T for T cell stimulation. I saw a not a POI's question, a question or something about that, so maybe that's something important to know. IL-3 is bone, so T-bone, so it is bone marrow stimulation. 4 is E for IgE production. 5 is A for IgA production. And 6, this part I think, inshallah, I'll probably know next time I look back in this video, but it says upregulation of obviously that's the wrong spelling, but acute phase reactants. So interleukin 6 is involved with the upregulation of acute phase reactants. But the more important thing right now is IL-6 is involved with fever and lymphocyte maturation. That's in terms of the acronym, mnemonic, whatever that is. Next, we've got these two, which are also very important. We've got interleukin 8 and 17. 8 is induces the neutrophil chemotaxis. I'll talk about this later. But basically what this means is the concentration of interleukin 8 increases closer to the infection site. And that helps to attract the neutrophil to the infection site. Then we've got IL-7, so interleukin 7. This is a pro-inflammatory cytokine. I'll talk about this in terms of T-cell activation. Okay, that's that done. Now let's go on to the innate response. So we're starting immunology basically. So innate response, this would happen, this part of the innate response would happen after the physical immunity barriers are breached. So first we've got 3 main steps. We've got detection, communication, and disposal. So in terms of detection, our macrophages in the tissues would detect PAMPs. PAMPs, I believe, is pattern associated. No, sorry. I can't remember what it was. But PAMPs, I forgot what it was. Basically, PAMPs is on the pathogens, and it's detected by the macrophages via our TLRs. TLRs are our toll-like receptors. I'll write in the comments what PAMP stands for, inshallah. Anyway, next thing is our communication. So our macrophages would then engulf the bacteria, thus they would release cytokines. And now these are the 3 main cytokines which I'm going to talk about. We've got TNF alpha. I think that stands for like tumor necrosis factor alpha. But basically what that's involved with is it's a pro-inflammatory cytokine. So it causes inflammation and it regulates cell death, and necrosis is like your messy cell death. Apoptosis is your programmed cell death, and TNF alpha is involved with that and regulation of it. Next, interleukin 8, like I mentioned before earlier, was that it induces neutrophil chemotaxis. Now I'll expand on that now. So interleukin 8 it tracks the neutrophils to the site of the infection by making a chemotactic gradient. So what this basically means, like I said earlier, is that it increases the concentration of interleukin 8 closer to the infection. Thus, it would help with attracting the neutrophil to the site, infection site. Next, we've got our interleukin 6. Interleukin 6, this is a growth factor for our B cells. So interleukin 6 would induce maturation into our plasma cells. Bear in mind, our plasma cells are involved with antibody production. Next, interleukin 6 would also help with enhancing T cell differentiation and cytolytic activity. I don't know what that word means. I'm guessing I'll find out later, inshallah. And interleukin 6 is also involved with a fever, as it signals to the hypothalamus to increase the body temperature, thus causing a fever. Now, like I'll just quickly summarize. So innate response, we've got detection, we've got communication, which is the macrophages engulf the bacteria, thus release your cytokines. Now we're going to go on to disposal. Now disposal, I've added a bit more information than potentially we need to know, but I like to know the mechanism. So disposal is split into 4 main steps. We've got adherence, ingestion, digestion, and excretion. So in disposal, our macrophages and neutrophils would engulf and kill the bacteria. The way this happens, I've also got a diagram which I'll explain afterwards, inshallah. So first step is adherence. So PAMPs, I can't believe I forgot what that means. PAMPs on the bacteria surface would attach to the receptor on the phagocyte, such as our toll-like receptors. So I'll go in the diagram afterwards. Next, after this, is our pseudopods, which are basically tentacle-like projections. They kind of just grab onto it and they engulf the bacteria, and this would allow for the formation of intracellular vesicle. Keyword is called a phagosome. The next step is digestion. So our phagosome fuses with the lysosome, and this would form our phagolysosome. The phagolysosome, the enzymes of the lysosome would destroy it and destroy the bacteria inside it. Final step is excretion. So our pathogen fragments, these are discharged by the phagocyte, and main reason of course would be this will allow the phagocyte activity to continue. So let's look at this in terms of a diagram. So over here we've got our the blue one is our PAMPs, and this is our toll-like receptor. That is our macrophage, or like our phagocyte, and that is our bacteria. So the PAMPs would attach to the receptor on the phagocyte. Then after this, our pseudopods, which are like our tentacle-like projections, they basically grab onto the bacteria and allow for it to be engulfed. And then this would allow for the formation of an intracellular vesicle called a phagosome, which is this thing here. After this, then the phagosome would fuse with the lysosome. I didn't know how to draw this, so the black part would be our phagosome. The red part is our lysosome fusing. Lysosome, of course, was one of our what's it called, organelles inside the cell. And now what this would form is our phagolysosome. And inside the phagolysosome, like I said, you have the enzyme secreted, and this would allow for the bacteria to be destroyed. Final step would be excretion. So the pathogen fragments are then discharged by the phagocyte via exocytosis. Great. So that is innate response. Now I'm going to go on to allergic reactions. So this maybe is a bit of a side venture, I think, or tangent, but it's important to know, I think, from like one of the slides. So now we'll be talking about allergic reactions such as pollen. These are involving our mast cells or our basophils. Wait, let me go up here. Mast cells or basophils. Let's come back to here. So we can link everything back together. So in terms of our immune cells, our mast cells and basophils, like I said before, they are similar. So the basophils, however, are found in the blood. Mast cells are found fixed in tissues, and these are down myeloid lineage. So let's go back to here. The allergic reaction, this is split into 2 steps. Our first step is our sensitization phase. This is basically our first exposure. Then our second step is our re-exposure phase, which is basically every subsequent exposure after the first. So the first time it's exposed to the allergen, the immune system may see it as harmful. For this reason, the body would overreact. This would trigger B cells to differentiate into our plasma cells, thus producing our IgE antibodies. Remember IgE, we're talking about allergy responses, and it also activates the mast cells. Now our IgE antibodies would bind to the IgE receptors on the surface of the mast cell or basophil. So our basophil mast cells have the IgE receptors on it, and then the antibodies would bind to this, and this would allow for the cells to become sensitized to the specific allergen. For example, pollen. So allergens don't always have to be harmful, like extremely harmful. They can also be stuff like pollen, I'm guessing. And then next stage is our re-exposure phase. So like I mentioned before, these are basically every exposure after the first. So the allergen then binds to the IgE antibodies on the sensitized mast cell or basophil. And then the binding causes cross-linkages of IgE receptors. I don't know how important this part is. So the binding causes cross-linkages of IgE receptors. However, this part is very important. Degranulation. I've also defined this. So degranulation is when the immune cells they would release the contents of granules. Granules are specialized vesicles, and this would be released into the environment. For example, we've got histamines, cytokines, or prostaglandins. And then degranulation would cause the release of inflammatory mediators. Like I mentioned before, this was the definition, so I'm kind of repeating myself now. But degranulation would cause the release of inflammatory mediators. For example, histamine. Histamine would cause vasodilation. Now, it's important to think why this would be important, as well as why vascular permeability increasing would also be important. The reason why is because this would increase blood flow to the area. Now that's important because the more blood flow, the more immune cells you'd have, so it's more beneficial, and it'd be like a faster response, I'm assuming. Next step, we'll be going on to our eosinophils. So eosinophils, once again, I'll go back to the diagram. My phone's heating up, lol. So eosinophils, yep, so once again, we're staying down the myeloid lineage. The previous video has a bit more information about eosinophils, but it's basically repeating the same thing, which is eosinophils are a phagocytic cell, and they're involved mainly with like parasitic infection. So eosinophils, of course, phagocytes, they would engulf and thus kill the parasites. And the way they do this is with its cytotoxic granules. Now let's go on to the activation of adaptive immunity. Now this part, it's not hard, but it may be a bit confusing potentially, so if it's confusing, then I'd need to like slow this video down if I'm watching on ×2. So the activation of adaptive immunity, this is involving our dendritic cell and our natural killer cell, also known as our NK cell. That's a little diagram of our dendritic cell. DC stands for dendritic cell, PRR stands for pattern recognizing receptors. So our dendritic cells have pattern recognizing receptors, and this would identify a specific molecular pattern. Thus, it would initiate the immune response over here. And upon recognition, so the dendritic cells would engulf, keyword, and digest the pathogen. Massive word here is process. So what dendritic cells would do is, after they've engulfed, so let's say we have a pathogen, the dendritic cell has engulfed this and is digesting it in the middle. Thus, after this, it's processing it. It's processing the antigen for presentation. And now you're wondering probably, where does it present it? Actually, before I get to that, after processing, the dendritic cells would thus migrate to the lymph node. This is very important. Now, the place where the dendritic cells would present the processed antigens would be on the major histocompatibility complexes, so MHC1 or MHC2. It's important to note that dendritic cells have both MHC1 and MHC2. So MHC class 1, this would be for our CD8 cells, whereas MHC class 2 is for our CD4 cells, linking back to the rule of 8. 1 times 8 is 8, 2 times 4 is 8. And what this basically does is this antigen presentation would activate the naive T cells, thus initiating the adaptive immune response. And as well as this, we also have our natural killer cells. Natural killer cells, they would kill cells by releasing cytotoxins, mostly involved in viral infections and cancer. Important thing to note here is that natural killer cells, if we look at it on the actual diagram, natural killer cells come from a lymphoid or like a lymphatic lineage. However, it is not involved in adaptive immunity like T cells and B cells. The reason being is because the natural killer cells are a lymphocyte, but they're involved in innate immune response, not adaptive immune response, because they lack an antigen-specific receptor. However, our T cells, for example, do have antigen-specific receptors. And for that reason, NK cells are involved in our innate immune response. Next section is going to be our T cell activation. We're about another 5 minutes, I think. So T cell activation. So in terms of our T cells, of course, we've got our, let's go back. We've got our CD4 cells, which then develop into our T helper cells. And we've got our CD8 cells, which then develop into our T killer cells or cytotoxic T cells. Now, our CD8 cells, they would form our T killer cells, like I said, and these are associated with cells expressing the major histocompatibility complex of class 1. And this would release cytokines that causes apoptosis, which is programmed cell death. Now, CD8 cells are more relevant in viral infections where the pathogen can replicate intracellularly. Next, we've got our CD4 cells. CD4 cells, these are activated to produce Th17, that stands for T helper 17 cells, in the presence of interleukin 6. So, like I mentioned before, so interleukin 6, this is also involved with our lymphocyte maturation, lymphocytes being our T and B cells. So if I come back over here, our CD4 cells, they're activated to produce T helper 17 cells in the presence of interleukin 6 as well as TGF-beta. TGF-beta stands for transforming growth factor beta. And T helper 17 cells would they'd release interleukin 17, which is a pro-inflammatory cytokine. And this would promote the secretion of interleukin 8. Remember what I said about interleukin 8? That is a interleukin 8 would induce neutrophil chemotaxis, meaning it increases the concentration of interleukin 8. The concentration of interleukin 8 would increase closer to the site of infection because it wants to attract the neutrophil towards the site of infection. And so the interleukin 8 would make a chemotactic gradient to attract the neutrophils to the site of infection. Important thing to note is T helper 17 cells that stay in the lymph node are called TFH17, also known as T follicular helper 17 cells. And that's in terms of our T cell activation. Next, we've got our B cell activation. So our B cells would encounter pathogens, and this would activate the B cells, thus causing our IgM production. Let's come back to here. IgM is talking about activating the complementary system and all this. It's a pentamer, it's antibody. Then our T follicular helper 17 cells would help the beta cells to mature further, and the B cells would start producing your antibodies. So in bacteria, the presence of interleukin 6 would lead to IgG production. Let's go back to over here. IgG is talking about neutralization and opsonization, and it also aids in the complementary system. And of course, IgG, goo goo gaga, it crosses across the placenta. Finally, we've got towards the end of the immune response. So at the end of the immune response, if or when the pathogen is eradicated, most of the T and B cells would die. And whereas your memory lymphocytes, for example, your mature T and B cells, would stay in the blood after your immune response, of course, because if they would be needed, then they'd be activated even faster. And that was I need to look at that back to see if that even made sense, but that is the immune system.